So here we are. This is my last lecture. So since it's my last lecture, so I might as well choose the topic, and I will speak of my pet topic, which is networks and performance, really the intersection of the two. But I will start by speaking a bit of history. Like when you get old, you become more interested in history. So I will start by saying a few words about the history or prehistory of the internet. And some of you who took my lecture or TA'd my lecture will recognize some of the animations I use in the first hour of the first course on computer networking. The first really development that led to the invention of the internet was the invention, before the internet actually, of packet switching, and it was a French invention. Right? And packet switching consists in saying if you have a big amount of information to send, you break it into pieces, and then why is that a good idea? Why did the networks at the end come out like this? Well, that's, you see, if you do what I call a performance analysis. Here's a performance analysis 101. This is a time and space diagram. On this direction you have space, on that direction you have time, and this is showing what happens if you send a message from A to B with an intermediate system in the middle that has to relay it. If you do the entire message, well, it takes longer than if you break it into packets, you gain time, and more importantly, what happens in the system in the middle is that the system in the middle has much less information stored at any point in time, which was really the true argument for this at this time. Now, if we're back in history, you see that the networks that were invented, there were several. And the internet, in fact, was a little thing in a corner, very little known, in fact, and not very widespread. The industry was using, I would say, two major internet networking technologies, SNA and DECnet. Most universities were using DECnet and small-scale enterprises, and the big enterprises were using IBM SNA. They were all using packet switching, and since I'm French, or Breton, I have to mention Honorary, which is also the French technology of that time. So that was the first thing. People who connected computers together had the idea of packet switching, and they had this idea because they did some minimal performance analysis. And then things went on, and there were several technologies that were competing, and as I mentioned, the major ones were not the internet. But the fact that there are several technologies was a problem. So a company emerged, Cisco, which is now the leader in communication technology, networking technology at least, invented what is called the multi-protocol router, which is an intermediate device that's able to handle all these different IBM, SNA, and also TCP/IP. And I joined the industry a few years after that, and the thing that we knew at B&R and at IBM was that the multiple protocol routers, they have one problem, and this problem is TCP/IP. That's the internet traffic that kills all the other traffic. So they had to do firewalls, weighted fair queuing stuff, and so on, to isolate this traffic. Why is that? Well, because the internet, the TCP/IP, when it was invented in 1974, it was invented very much in the folklore things of that time, hippie style, I would say. You just do it, and you have a lot of fun, and you're happy. And then you see what happens if it doesn't work. And in fact, there was a major bug. There was no congestion control. All the other techniques, I mean, the industrial ones that you sell to big companies, you make things that don't break, so they knew, and there was window flow control or some form of congestion control. The internet did not have, and then, of course, what happens is, when it became a little less little, it collapsed. In 1986, there was internet congestion collapse. The remarkable thing, I think, is the remark that the people who were behind that did when they observed that. They say, oh, I was fascinated by this sudden factor of 1,000 drop. Right? So they were surprised. They were surprised that the thing that they are constructed was not working, which is how TCP/IP protocols were developed. Perhaps that's the reason why they conquered the world, because they just did it, whereas the others were more serious and tried to make sure everything works well before deploying it here. So there was a problem. The internet collapsed. It was no big deal at that time, because in '86, the internet was just interconnecting a few experimental sites in the world. And as you see, the throughput dropped from 32 kilobits to 30 bits per second, so no big deal. Why did it drop? Well, because there was something that in performance evaluation we call congestion collapse. So here, a bit of a technique. You can imagine a network, to understand how it works, imagine a network that's a ring, and imagine that in the ring, at every node, there is a source of traffic that wants to send it to another destination, which is not on the same node, but a bit further out on the ring. So you have one flow here, and at every node, you have a similar flow. And now, what happens if everybody sends into the network without any control, without any regulation, essentially? Then, which means if sources can send as much as they want, which, believe it or not, was what happened in the internet at the beginning. Well, I'm plotting here the result of that. On the x-axis, you have the input, how much the sources are sending, and on the y-axis, you have what comes out, the output they use. The rest, of course, is what is lost here. We see that as long as sources send a little, not too much, then what comes out is equal to what comes in. We have a linear increase until you reach the capacity. When you reach a capacity, you have congestion. You cannot send more, you cannot do more than the capacity of the system that you have. That's natural. But the expected behavior, which was the behavior of the industrial networks, was that when you reach the capacity, well, what comes out is approximately the capacity, and the difference between what was sent and what comes out is what is lost. But the internet didn't do that. The internet collapsed. That means the more you send, the less it delivers, which is a bit like us when we're flooded with emails. We have so much thing. You ask us to do more work, and at the end we do less because we spend a lot of time in context switching, for example. Here the reason is a bit different. The reason is that in a network like this, if you have a lot of losses, then you accept into the networks packets that consume some resources. Those packets most of them will be dropped further down, but you don't know that they will be dropped, but you use resources to serve them and send them somewhere else where they will die. So by doing that, you devote resources to units of work that will not complete. That's an ingredient of congestion collapse that we studied in one of the courses that I gave until very recently at EPFL, until yesterday. Then, since the internet was fixed, after the collapse and the observation of the collapse, the person I mentioned, Van Jacobson, who observed this collapse, fixed it. Eventually, the fix consisted in copying what was done in DECnet, even though at that time they were not knowing that they were copying it, because the internet was a very, as I say, marginal community that was living a bit outside of the industrial community. So they implemented what is called congestion, additive increase, multiplicative decrease, and that solved the congestion problem of the internet. And since that problem was solved, the internet has been continuously growing. There were a few things that were missing before making it the success we know today. We needed, before, at the beginning, the internet was for the happy few who could type in command lines in the computer. You had the computer was just one screen with text, not very fancy. You could play Super Mario or a few things like this, but nothing great, a single window. And you could type command lines to say hello to a friend at the other side, at the other end of the world, a bit like a chat that we have today, but we had only one chat, one single app. That was the internet. Before, a number of things. Those things are three things, essentially, that the internet protocols were included into the mainline computer systems, the Mac and the IBM PC, or the Microsoft PC, I should say. So Microsoft adopted TCP/IP in '95 natively, and Mac, as you can assume, a bit before. And the second thing that was missing was HTTP, HTML, and the Mosaic Netscape Navigator. That's what everybody knows today, Safari, Internet Explorer, Chrome, etc. Those things that seem natural today were a complete revolution. You could only click on something and open a link and open another window, and it was marvelous. Before that, it was not possible. So now everybody can use it. So you could have websites for pizzerias and so on. That started in '94. 94 is also an important year, at least for me, perhaps not for the history of the internet, but for me, because this is precisely when I joined the internet. So when I joined EPFL, I came to EPFL. That's exactly at the time where the internet was booming. So I created the lab called LRC. At that time, we spoke French at EPFL, Laboratoire Réseau de Communication. I started it with Yvette Dubuis. And a bit before, I was hired at EPFL because before that, the Section Système de Communication, which you see with this French flag because it was partly located in French, was created 3 years before, notably with Jean-Pierre Hubeau, who's here in the room here. This had a large impact on what we did at EPFL. So when I joined EPFL, I started the first TCP/IP course. It was called a bit differently here. And we did the first labs with TCP/IP. So this is one of the very first labs devoted to what was called, in '96, the new Internet protocol. It's called IPv6. And because when IP was created, hardly was it created that in '95, in fact, people realized there's problems with the address space. So we need a new version that was done, called new, in '96. Since '96, my largest failure at EPFL is that it took 25 years to have IPv6 supported by the network of EPFL. But I'm happy it happened before I retire. We had other protocols. We had ATM, like Patrick mentioned, which was meant to be a higher speed than IP, than TCP/IP. And also we were assuming that we could do reservation protocols, and we would do that kind of things. So because now the internet was really becoming mainstream and performance was an important issue, there has been lots of performance optimization that were done. One of them was ATM, a technology that was really super cute and high speed, and but was not really available on the Ethernet switches and the software systems. So Werner Almesberger and Philippe Exlin here and we developed a technique that was recognized by the ITF that became an RFC and has a Latin American name because Philippe was returning from a vacation in Peru, I believe, and gave it the name to this protocol. That allowed to use ATM de facto on standard computers. That was also implemented by Werner in the Linux distribution so 25 years ago. By curiosity, a few weeks ago, I checked whether this distribution is still alive, and it is. So there was a request for a change 1 month ago that was addressed, and so that distribution is still working and is alive here. Sylvia also joined us on this to deploy this in a text bed called the Expert. So we deployed in a European project all this technique here. Sam studied on the side whether we could do better to support IP traffic natively on ATM. And Werner tried very hard to get rid of ATM entirely and do the things natively with IP, which eventually is what happened. And since, as Patrick mentioned, since we were serious about ATM, we did also the first pre-Zoom, pre-COVID, pre-everything remote teaching lesson. So one colleague at ETH, Bernard Plattner, was on sabbatical, so he wanted to have somebody to replace him for the lecture. So we had this idea. There was a project, Telepoly, started by Jean-Pierre Hubot before, and they were looking for something to do with Telepoly. So they volunteered me to do something. So I gave a lecture, a true lecture for a full semester at 2 places. So I was the first virtual professor, if you want. I was both in Zurich and at EPFL. Sometimes I went to Zurich physically, sometimes most of the time I was at EPFL. And so we had a class of students in Zurich and in Lausanne. You can observe the technology that we had. So the screens, there were CRT TVs and nothing to do with the beamers that we have here. But it worked. We used ATM and we had very good quality. The audio was perfect, no delay, better in fact than today's technology of internet. It was very interesting to have this simultaneity, so the absence of delay. We had 20 millisecond delay passed between Lausanne and Zurich. So I could observe the different reactions in Lausanne and in Zurich. For example, in Zurich, 5 minutes before the lecture, the room is full and everybody is ready. In Lausanne, when you start, you have first go out and close the door to give the signal that now all those that are still chatting in the corridor should join. So it was very obvious on the screens there. ATM and reserved services were one of the hot topics at that time, whether in the form of ATM or reserved services without ATM. And that led also to a theory, which is now called network calculus, which I developed with Patrick Tirant here. And this all started with a seminal paper by René Cruz in San Diego called The Calculus for Network Delay. His paper was really seminal, but this guy was a genius. Unfortunately, he passed away, but he was not very good for titles, so he called it a calculus for network delay. So I studied his papers when I arrived at EPFL, so as you see, 5 years later. And I found that there's a way to simplify it, so I called it Network Calculus Made Easy, and perhaps the major contribution was to change the name and call it Network Calculus. Of course, there were a few more contributions, which was to make it more abstract, so I introduced the formal definition of service curve, and also I cast that as an algebraic approach, which allowed to make it systematic instead of ad hoc like it was here. And that became a great success. And we wrote a textbook that became the reference for this topic. So what is network calculus? Well, that's something that explains and quantifies queuing properties. For example, burstiness. What is burstiness? Well, burstiness is here is 2 packets that are sent by perhaps a video conversation over the internet. When they go through a networking system, a router, an intermediate system that forwards the packets, then the nice spacing that you may have between packets might be changed here. You see that there is a burst of 2 packets that come end to end, which you could say, well, no big deal, but yeah, but it makes the queuing in the next hop worse, so it makes groups of things that are not good. So to quantify how much more burstiness there is, that's the kind of things we do with network calculus, and a number of other things. For example, with Olivier Verscher, we studied how we can quantify and size the playback buffer for video systems that work over such services. With Gianluca, we studied the stability and delay bounds in large-scale networks. If we have limited burstiness that is acceptable, how many flows can we accept? And with Sylvia, we also studied how to make more dynamic systems that would be able to adapt here. But perhaps more interesting here, or more anecdotal, but more is the dispute. There was a dispute very much in the Calvin style, in the terms of style of religion. There was a dispute between did Mary really this and that. So there was exactly something like this at IETF. IETF is the body that standardizes the protocol of the internet. And the very funny thing is that it's a democracy. So people are sitting in this room here proposing a new way to do something, to do a new type of service, a new version of TCP. And then the people in the room come and give their presentations. And if there is disagreement, people vote in the room to see, do we accept A or B? That's the way it works. That's fancy. That's the, I would say, the tradition of this TCP IP thing. So there was a first definition of an advanced service, something that would simulate over TCP IP what ATM give, called the expedited forwarding service, that was proposed by Van Jacobson. Van Jacobson is this guy who fixed the congestion problem after being amazed by the fact that it exists. So since he had obtained such glory for fixing the congestion problem, he had a lot of credit, and he proposed another version of expedited forwarding system that completely ignored those burstiness things because he did not read network calculus. He was a VP of research at Cisco. So very important, #1 company. Then I was approached, funnily, by people from Cisco in his organization who came to me and say, help, we have a big problem. Our big boss doesn't know what he's speaking of, and we need help from experts to prove that he's wrong. So they approached me. I visited Anacharni in Boston, and we worked to prove that, yeah, it's not possible. If we apply this formula to an arbitrary network, we can have arbitrary delays and not the low delay that they were claiming they were doing. So there was a memorable meeting in San Diego where Anacharni and I and a large number of people, because everybody except those 3 guys agreed almost that this was wrong. We proposed an alternative, and this was adopted by vote, not a popular vote, but the random vote of whoever technicians were there, and that changed the definition. So it settled the dispute, and it was easy to do, not because we had the technique and the technology, and some people, like the technical people at Cisco, were aware of that technique. So network calculus was really invented for the guaranteed service internet, and I worked on that for a number of years. Then the guaranteed service internet, after this dispute and other things, was more or less settled. And as I will say in a few more minutes at EPFL, where we never stopped, we kept moving and we started new projects. So I stopped working on network calculus, but it lived with a life of its own. And in particular, the Airbus, the aerospace industry, had the problem of, this is a drawing that is trying to illustrate that one of the problems in an aerospace is the cabling. There's plenty of cables in an airplane, and reducing the cable is possible if you replace the cables by Ethernet. But Ethernet is for computers, it's not really for control and command, which requires very stringent quality of service. But with appropriate control, you can make Ethernet having the same property as a full cable system. But here, it's not like at the ITF, you don't vote in a room and people say, yeah, we like you or we don't like you and we accept this. Yeah, fortunately, it's a bit more serious because we fly in those engines here. So there is what is called certification. So you need to prove. So the Rockwell Collins was developing this Ethernet system for Airbus, and they had to prove that it's possible to have exactly what they say. So they tried for 1.5 years very hard, and they approached people who knew of network calculus and used network calculus and worked on making the proofs. And they also proved that the worst case delay bound that are obtained by network calculus, or the bounds that are obtained, are very close to worst case. This is an example of the network that's on board an Airbus, and to which these technologies were applied. So that was towards the end of the 90s. So at the same time, we had an effort to streamline our operations. So Jean-Pierre, Alain, and I created what we called an institute, which is just a collection of labs. And here I would like to honor Alain's memory here. Unfortunately, he should have given his honorary lecture 2 months ago, and he's not here with us to enjoy, I hope, this lecture and to enjoy what we could do post-retirement. This lab was later joined by Patrick Thiron, who was incorporated in the lab, but not yet as a professor, and then became professor of the lab, and Matthias Kogsgauser, who later joined it. So we had our own logo, our own everything website. It was really fantastic times to do such things here. In parallel, EPFL was undergoing tremendous changes of all kinds. So Section Système de Communication was created, which was a weird thing supported by the 2 departments. I was in the computer science department. Colleagues were in the electrical engineering department. It was a lot of orthogonality and complicated things. And here are perhaps some of the milestones. We created the first the graduate school, which was called the pre-doc school at that time. Which, believe it or not, did not exist at EPFL. We also started a full-fledged premier cycle, because before that, our students would come from other premier cycle. Then we also did a full-fledged curriculum that made it possible to live without Eurecon, which we did a bit later. In the meantime, we created the department DSC, Département Système de Communication, which was the logic of the way EPFL was at that time. But 2 years after, it was merged into a school because there was a big reset called Ebicher that came into the room and reset everything. And I had the honor of closing the department because I was department head for 3 months. I was from 1st of October, I was elected department head. And 1st of January, we said, no, there's no department. You have to, you don't exist anymore. And before that, we had the time to start. I mean, it was the submission started in '99. There was the submission of the MIX program that was funded, a big research program that was funded, and I'll say a few more words about it a bit later. Now, the internet was done. Reservation services were done, so we were wondering what to do. Well, so we made things more complex, or in some sense the networks naturally grew more complex. So we worked on a number of topics. Here's one of them, which is called failure propagation. In a network, you want to have redundant links because you don't want to stupidly lose connectivity because there is one road construction somewhere that breaks a cable, so you want to have multiple cables. And you do this by having, for example, this is a network planner. We'll see between A and B, I have a link, but I have a link between F and B. So if I need to go from F to B, I can go via A, or from A to B, I can go via F, etc. That's the view that system managers have of networks. But in reality, things are complex, and links are sometimes made of other links of another technology. For example, you put optical fibers into plastic pipes, and those plastic pipes may contain several optical fibers. So you may believe that you have redundant optical fibers, but they're in the same plastic pipes, and if they're cut, they will be cut at the same time. So that's the problem we addressed here by solving design methods that would avoid what is called this failure propagation here. We worked also on high-speed routers. That was a joint project with IBM and Lukáš to use what was called at that time network processors to make the network faster. As Patrick mentioned, we worked with Paul Hurley and Patrick on a low delay service. The quest for low delay is a quest that is not finished. We're still trying to have low delay and guaranteed service in the internet. So one more attempt here was to combine without any reservation system with blue and yellow, with blue and green packets. It was a lot of fun at that time. We have seen that it's essential for the internet to have congestion control. Congestion control is in the TCP protocol, and many applications, particular multimedia applications, emerge that don't use TCP. So if we do nothing, there would be, again, a congestion protocol problem. So that was addressed by Milan Vojnović, in particular, who did a test bed to evaluate a number of proposals that were implementing congestion control, and we found some surprising results, that things are not as easy. And Catherine Boutremont and Jörg Widmer, who unfortunately can't be here today, also worked on this topic. Now, once you start building all those things that are very complicated, one key question that arises is flow anomaly. So with Mark and also another IBM project, we work on detection of flow anomaly to try to do diagnostic of bad things that can happen in the network. I mentioned MIX. MIX stood, I believe, for Mobile Information and Communication Systems. Thank you, Jean-Pierre. So that was a major project launched by Martin Vetterli and directed by him, and where the idea was to federate all the research done in this emerging department that quickly became an emerging institute of a faculty. And one of the issues, so this term was coined, I believe, by Jean-Pierre, terminode, so having what is now called ad hoc routing, possibilities to use the devices to route without infrastructure, which is one of the things that is used today in disaster recovery. It's used in war area, for example, or or construction areas. And we did the very funny things, like we had a game where students visiting potential EPFL students could do a game and play with different routing strategies to see what works better in this potential area, which has a big hole in the middle because probably there's no boat on the lake here. We worked on other routing system with Silvia and Ljubica. We worked on, so this work was a work of Ljubica and with Ljubica and Silvia. With Ljubica, we worked also on related topics in the distribution of multicast, a topic that became very important later in data center, and we developed something that 20 years later became the beer protocols for data centers. We also deployed, so those mobile ad hoc things were deployed by Aladdin El Fawal in collaboration with a group in Patrick's lab, where the problem was to test this epidemic dissemination. So Aladdin installed 20 or 30 Wi-Fi stations with a battery, put them on bicycles, and had some of them stationary in the corners. At that time, we could place like this everywhere in the corners of EPFL. That was fantastic. And just put a sticker in case of problem, call X, and that was good enough. And we could ride along and measure the performance of mobile ad hoc routing, which works perfectly well. Measuring the performance is one thing, but designing what the performance criterion is a surprisingly difficult topic. that is often ignored, but is important because you need to know what performance criteria to choose when you design your protocol. So Bojida did a landmark paper that showed that essentially how to compute min-max and max-min fairness, which is one of the classical metrics to be used, but also showed that for many protocols of interest, it might not be the thing of interest, so you might need to add some additional tweaks to it. We also worked on peer-to-peer systems. That was a joint project with Fabius Clem and Karl Haber, where here again, as you can see, some continuity in the topics at least. The problem was how to avoid congestion control. Congestion control and congestion collapse is something that you do in any system. If you build any complex system and you don't make sure you can avoid devoting resources to units that will not eventually complete, your system is likely to collapse under congestion. So we repeated the exercise here in a very different context. One of the big focus that was a lot of fun was to work on ultra-wideband. Ultra-wideband is a technology that was emerging at this time that you have now in smartphones they're used for localization. It can be used also for short-term communication. And ultra-wideband means that the spectrum of the communication is very wide because it sends peaks of information. Having a very wide spectrum means that it's possible to have what is called quasi-orthogonal codes, essentially in a more standard language. It means you can send multiple signals at the same time. If you randomize them, because the number of dimensions is so large, they are quasi-orthogonal, because in a Euclidean space, a very large dimension, any two random vectors are almost orthogonal, which is a bit counterintuitive if we compare to our small dimension spaces in which we live. So that gives the idea of a medium access protocol that essentially lets everything happen. So for example, when B sends to A and C sends to A, if you use Wi-Fi and A and B are both, C and B are both sending at the same time, there will be a problem, there will be a collision. Perhaps both communications will be lost. But here, if A knows that B is talking or A decides to tune to the code of A, then whatever someone else is sending does not really hurt the communication, which is illustrated by those little bubbles here. So this protocol was designed, so the theory for that was started by Bojida and was designed by Ruben and also analyzed by Manuel and Aladdin, who worked on the signal acquisition part, how to detect those peaks that we see in the signal. And it was implemented and designed in discrete components by James with the complicity of Catherine Deholin and Stéphane Robert and Agnieszka Kiwerwik, who did the antenna. And this is the test bed. So this is one system. So as you see, it's a bit bigger than what we have in our smartphone today. But we showed with that, for example, that we could have multiple systems talking at the same time and nobody would feel any collision, in fact. So those was all patented and sold here. As Rüdiger nicely mentioned, once you have a tool, you tend to apply it to many things. So since the performance analysis of computer networks is very similar to what you can do with other things, and since security is always looming ahead as soon as you do something with network, it was quite natural also to apply performance analysis to the security issue. So this was started with Sonia, who unfortunately cannot make it, and work that was later continued with Jochen Mundiger, where we analyzed reputation systems for mobile ad hoc, because you cannot simply assume that you would rely on others to relay your information. You need to somehow keep track of what is happening. And this was a mechanism that has been deployed and invented by Sonia and is part of his PhD thesis. It had a number of statistical problems to solve that were solved with the help of Anthony Davison. And that was really great fun and gave a lot of very interesting papers. In the same vein, when we did ultra-wideband system, we can use them for ranging, and ranging means that, for example, if you're trying to connect or paying contactless, then you want to make sure that when you're paying, you're really paying to the object in which you're paying, that you're not actually transferring your credentials or the payment to another object. So you believe you're paying your sandwich at the cafeteria, but in fact you're transferring money to someone who's waiting in the queue behind you. And the cafeteria says, hey, when do you pay? You say, oh, but I've paid. No, you haven't paid. And so this is what is made possible, what is called a distance decreasing attack, which play with the subtle fact that in ultra-wideband system, the signals are fairly long. And most of the time, this is where performance kicks in, most of the time, we need the signal to be very long because in the worst case, a less long signal would not make it through. But most of the time, a much shorter signal will make it through, which means that you can anticipate the signal and not wait until the full signal is received to do something. Sometimes it will fail, but when it succeeds, you have managed to take less time than the system assumes it will. So you're shortening time. Shortening time means you're shortening the distance, and this is what will make your CamiPro money go to someone else's wallet here. This is a general, one of two problems that are related to general problems of privacy. And privacy is one problem that we're all concerned with since our devices are tracking us. Now, if you do nothing, if you allow the default settings on Google, Google will know this of you, for example, will know everywhere where you've been. You can ask it to have lower accuracy, or there are systems, so-called privacy-preserving mechanisms that will try to prevent your privacy. But the difficult thing is to really quantify them, and the landmark paper that was a great pleasure to be done with George, Jean-Pierre, and Reza was exactly providing metrics for this and how to define exactly what one should measure when we are pretending that we have a protocol that's preserving the privacy. Rudiger has mentioned also Patrick has mentioned my work on mean field. This came from a problem that most of the time the techniques that we use when we model communication networks are Markov chains. So Markov chains are graphs that you can draw like this. If there's a small number of states, then you can analyze it using the standard theory of Markov chains. So this is, for example, a representation of the MAC protocol with the bubbles that I've shown that was designed by Ruben Mers and implemented by James. So you can analyze it in this ad hoc way. In fact, this is my first PhD, 96. Took only 2 years to do. I joined in 94, and I had a PhD student out, Stéphane. But I was cheating a bit because he had started the PhD before I joined EPFL. He knew I would come, and he had anticipated. So Stéphane's thesis was exactly on applying Markov chains for modeling communication systems, and this has been also applied a lot by Sam to the performance of TCP here. So that was a long history of applying such techniques for communication networks. But when we started doing these ad hoc things and networks grow more complex, we have many, many, many objects, and then those systems don't scale, so the equations become untractable. And so I went to a field called statistical physics to see because they have exactly that kind of problems, and borrow the techniques here to write what is called a macro-level equation that I'm illustrating here on a fairly small scale example to see what can happen. Here, that's an example of how we had to model virus infection, where standard viruses are not just infecting you. I'm talking of computer virus. They first infect you and then they do nothing, so that you don't realize that you have a virus. Because if they infect you immediately, you know there's a virus, your system is dead, and that's not what the darknet wants. The darknet wants to infect you and decide when the infection will come to play. So the viruses are dormant. And this is trying to show the dynamic of an infection of 1,000 infected computers, depending on the time constants and how the waking up arises. So the green thing is a simulation here, and you see that depending on the speed at which some of the things happen, you either have convergence to something where the virus infection stabilizes, or there is a cycle here. But knowing that there's a cycle is something that's very hard to do when you have that kind of model, even though there are cycles everywhere here, because you typically do simulations and you look for the steady state. Steady state means you run the simulation, you're influenced by the initial condition, then you run it long enough, and when it's long enough, then if it's long enough, for example, you get around this point here. But you can do another approach which translates, if you have a large number of objects, 1,000, then you translate, you don't look at every object individually, but just you count how many objects are in which position or in which state, and that gives you a radically different approach. Here, that's an ordinary differential equation. In other case, it's, in general, it's called the Makin-Vlasov process. That's a process that contains the distribution of where the systems are. And in this case here, that looks more complicated, but that's way more simple. This is simple to express, but very hard to run. You need mega supercomputers to simulate things. Here, it's more difficult to express, but physicists have been, and mathematicians, of course, have been doing that for decades, and you can solve that numerically, and this is what you obtain, which is a smooth approximation of that, but has other properties. In particular, you can analyze whether there are oscillatory behavior. So the presence of oscillatory behavior is something that was completely ignored in all the models that were done of communication networks, and in particular in the analysis of the Wi-Fi protocol, the protocol that we use here in this room to access the Ethernet wirelessly. But some people had observed that there are oscillations. So here we can find oscillations at the time scale of 10 or 20 seconds that are predicted exactly by this mean field system. So that was work that was done with Jong-woo, who was a postdoc from Korea. We also had a very funny work. Again, we applied this with Nicodine, and who was my PhD student, and Augustin was working at Technicolor when I was doing spending a sabbatical at Technicolor. So we applied this to the dissemination of information, a bit like the terminal across the lake of Geneva, but to make it more fancy, we put it in the Bay Area, where it immediately got published at Symmetrics because it was the Bay Area. And so we can have the Makin-Vlasov process, which is now a PDE, partial differential equation, that in most of the time a PDE is not much more fancy and you cannot do much, but this one has a special structure that could be solved, at least reduced to ODE, for which there are efficient solutions. So that allows you, for example, to say if you want to carry information across an area and you want to facilitate the ad hoc transport, so when two cars meet, they could exchange some bit of information, and you want to facilitate with putting a few base stations here and there, then this will exactly give you the dimensioning, and that was patented and used by Technicolor here. Back to security, the same techniques were used for what is called the age of pseudonyms with Julien and Hossein and Jean-Pierre, where we had exactly similar equations for calculating the age of pseudonyms that are used in mixed zones for anonymizing here. And that can be used to quantify, again, as I mentioned, the privacy that we gain here. The same equations can be used if we look now at many, many little things, and the many little things are packets, to clarify what was happening with multipath transport. Multipath transport is what you do if you use, for example, you're at home, you have your Wi-Fi at home, but perhaps you also have cellular network, or you have your mainland connection and your cellular telephone. You can perhaps use both for speeding up things. So companies like Swisscom are offering this as a service here. So when you do this, and you will run TCP over multiple paths here. Again, when you do this, congestion control as defined natively was not defined for this, so you need to somehow redefine it and do it and analyze how it was done. But people were struggling to analyze this because they did not have the right equation. So we applied with Ramin, Nicolas and Miroslav, we applied our modeling techniques to this, and we could find that the proposed solutions had problems. They were not even Pareto efficient. That means that they're not really solving the congestion problem, and having the equations made it possible to fix what had been proposed, and this was also ported to the Linux distribution as a standard solution. Now, once you start speaking of infection, large-scale systems, and then you're very close to the beauty of EPFL is that you're bombarded with announcements for seminars and so on. So, and if you're a bit curious, you still read the abstracts, and you realize that at the end of the day, there were quite a few people that were working on very similar things, except they never applied to communication systems or computer networks, but they applied to biology. So the idea, the beauty was to realize that the same Markov techniques, they use different technology. They use the Gillespie model instead of Markov chain or Markov processes, but they use exactly the same techniques. So I was a bit bold at that time. I think I was still young, far from retirement, so I thought, let's do something fun. So I went to Jean-Pierre Créhenbuhl, professor at UNIL, and as you see, the drawing was, there was not no DALI to do. I had to do the drawings myself at that time. So here you're showing a medical doctor, and that's supposed to be me, a geek with equations, who hand in hand, we gave a course at EPFL called Modeling the Immune System, where we analyzed all the papers and all the equations that are in a number of papers here. That was great fun. That even gave rise to Irina's thesis. So Irina used those techniques, and here's the kind of things we can do. She could, for example, sort out between hypotheses that were made on the amount of regulatory T cells. So T cells are cells of the immune system. The regulatory T cells, those are the cells that prevent autoimmune diseases, for example. And they are essential for patients that receive organ transplants. And biology is not like a communication system or computer science. People are still struggling about the hypothesis. So we're modeling things, but we're not too sure about. So here it was a radically different exercise. In computer systems, we're not too sure because there are so many details, but each of the details is known. It's just that we don't know how to put them all together. Here there were several hypotheses, like, so here 4 scenarios about how these cells are born, or where they are educated in the human body. And we simulated long life, the life of patients, compared to cell cultures that were performed by Laura Codari and Prof. Pantaleo's group at CHUV. And we compared what the models were giving. And so those are the famous confidence intervals that Rüdiger mentioned. And you see that there's only one of the models that nicely fits in the confidence band. So that is how modeling can help eliminate at least 3 hypotheses in this case here. Now, since we are very greedy, once you know a technique, you want to apply it everywhere. So doing this work required learning how the immune system works, which is an incredibly complex system, far more complex than everything I've seen before. But a simplification of it can give ideas for what is called an artificial immune system. So very much like there are artificial neural networks that are giving us ChatGPT today, which is much less good than a natural neural network because we need a huge network to learn. We learn more reliably, but the performance is less good. Here it's very similar. We can build bio-inspired immune systems that are able, for example, to do anti-spam or detect anomalies in mobile network. And that was the work of Slaviša that was also patented. Simulation is one of the key techniques that I've mentioned several times, and that is used all the times for evaluating systems. Here's a little history. When one of the routing protocols that was developed for ad hoc systems, you remember the Terminus, or the thing post-disaster recovery, or Caterpillar, when they do a big construction somewhere, they want to communicate between all the trucks, and there is no infrastructure, they're just moving objects here. So the IETF standardized also that kind of things, and there were many competing groups, and competition was very fierce. We didn't reach it to that level of competition. Our protocols, we didn't have the resources to propose them to IETF, but we observed as part of the research what was doing there, and IETF had a benchmark. So benchmark is a simulation model that everybody should use to compare the performance of different systems, and then you apply your benchmark, you show the results, and then people in the room vote on who has the best results, and this one becomes the IETF standard here. But the benchmark that they gave, which was the random waypoint, which is here illustrated in a simulation that was done by Milan Vojnovic. So you have roads, for example, or areas where you can move, and the mobiles, they decide on the location where they go. They decide also on the speed, and they go there. So initially, for example, all the mobiles choose uniformly with equal probability all the places where they go. So on the x-axis, you have the different segments, and on the y-axis, the probability. And they choose also the speed at which they go uniformly between a minimum speed and a maximum speed. So if you sample the system at this time, this is what you see, or shortly after the beginning. Then people have done that, and they say everybody should have the same simulation length, 900 seconds, and we compare your protocols. But some people, by curiosity, including us, by curiosity, we run the simulation a bit longer, and we saw that if we run the simulation longer, then things get weird. For example, the distribution of where the mobiles are changes over time, and the distribution of speed is not at all the distribution of speed that we had chosen initially here. And so the results were non-reproducible. And in fact, this was an example of a Markov model, a complicated Markov model that had no stationary regime. So absence of stationary regime means there is no really fixed benchmark that you can use. And this we could fix together with Milan Vojnovic and the complicity of Pierre Brémaud and François Baccelli, who were the experts in a technique called pound calculus. That's one of the techniques used for queuing networks, and queuing networks is one of the techniques used for performance analysis of communication networks, so everything is not far. So using those techniques, we could analyze this model and see, oh, it's broken. Using pound calculus, we could see that it doesn't work, and we could fix it and have a benchmark that could give a reproducible result. Here's an intuitive idea of why those things are the way they are. You start your mobile at a given point in time, and you pick at randomly a speed between 2 meters per second and 4 meters per second. Then you run the system, and you come back 2,000 seconds later, and you observe the speeds at which mobiles are. This is what you will observe here. And people were surprised. So the surprising thing was that people were surprised, because if you use pound calculus, you will see that that's quite normal. The distribution of speed here and there are related by an equation of this kind here. And I will not discuss the equation, but intuitively, what happens if you do such a simulation model, sometimes you pick a low speed, sometimes you pick a large speed, but if you pick a low speed, you're stuck with the speed, you will keep it long. So you will spend more time with long speed. It's what I call the cyclist paradox. If you do a tour on your bicycle from here, you do a tour, so 50% you're going up, 50% you're going down. But when you come back, you have the impression you were always going up, because you spend more time going up than going down. Right? So even though it's completely balanced, but in time it is not. That's exactly what's happened here. So as you see, it's fairly trivial, put it in this way. Now putting it mathematically is pound calculus, and pound calculus removes the sampling bias. That's one example I like, because that's one experience we always do when we take the train or the bus. For example, we had a dispute. In fact, the photo that you see where I am on the bicycle at a railway station, that's a dispute with the train company that doesn't care very much about cyclists. And they also claim that whenever they are late, this happens very seldom. Only 5% of the trains are late. But when you take the train, you experience that you're late 1 out of 3 times. So are they cheating or not? Well, they're not. It's just a sampling bias again. It's just that most of the trains that are late are the trains that have lots of passengers. They are the trains that you are taking, and not the trains that in the morning are empty or in the late evening are empty. And those are not. So this is called pound calculus and removing the sampling bias. Sooner or later, everybody realizes that we have a climate change problem. So we did it in the networking industry, I would say, 15 years ago, where networks started to go green. I think many people were aware before that. But before that, I would say beginning of the 21st century, we were believing that, yeah, it's a real problem, but it's not our problem, because we, in computer and communication systems, we consume so little, and we can do so much for solving the climate change problem. Until we realize that at the end of the day, we start consuming a lot. And in fact, once we get used to having wireless everywhere, it's much more expensive in terms of energy to place a telephone call over a wireless infrastructure, like we all do today, than over a wired telephone that we had many, many years ago. At least 100 times more expensive in terms of energy. So the energy consumed by the cellular networks is becoming a problem. And you see companies like Swisscom that are advertising that they are green. So we worked on the Swisscom network to do things like optimizing the association of users to cells. This is what we do if we don't optimize. You see that users are always associated to the nearest cell. But if you're a bit smarter, you allow to combine macro and micro cells. Then you try to associate only users to long-distance cells, in particular in the off-peak hours, which will allow you to shut down a number of cells or amplifiers. And that is one of the techniques that is used today in all cellular networks to adapt the power consumption to the traffic here. So this was done, this is work that was done with Miroslav and Lukáš. Lukáš, who I mentioned before, did work as a PhD student and now appeared here with another role as a professor, and that was a European project that we worked on that here. Tech also worked on a similar problem, where the problem here was more to optimize 4G and LTE parameters to reduce the overall consumption here. We also used the ideas with Nicodine and again Augustin and Vijay of using the mobiles themselves. If you have very, very frequently used content, it's very likely that it's available all around. So instead of downloading it repeatedly, you might download it from what is also called hot zones here, and that would save a lot of the energy here. So that was the branch saying, let's try to do what we do as optimally as possible from the energy viewpoint here. And we went also one step further, on beautiful papers, I found them beautiful, with Dan, where we managed to marry network calculus with energy. So marrying your pet topic with your, perhaps what should be the politically correct priority, by addressing the problem how flexible data center with battery storage can support the grid by scheduling their power consumption. So if the traffic in a data center is not completely continuous, but has a pattern that we can measure, then we can dimension the battery and such that we can get from the grid, for example, this red curve instead of the blue curve, which would help the grid, for example, shaving the peaks to facilitate, for example, the penetration of solar panels here. We also went, so that was, I would say, still in the communication and computer systems. Then here, I would say, we really moved one step on the side and followed a group of people that are called the ACM e-energy people, where some people believed, and still believe, that we can apply some of the techniques that are used in analyzing the performance of computer and communication systems into analyzing energy systems. I think the politically correct way to say is that we could analyze the same techniques. The other way to say it, instead of wasting your time trying to optimize the last % of efficiency in data processing system, why don't you apply this to optimizing energy systems? And it turns out that it is possible. At least we did a number of papers here with Nicolas Gast and Dan, and also Alexandre Proutier of KTH on, for example, analyzing systems that are buffer systems. For here, that's the how to buffer wind energy for the UK. That was a simulation done for UK grid on how to dimension and what policy should be used for storing energy in a pump hydro system. And we see that there is a sharp knee here. That means as a function of the amount of reserve that you have, then you should operate at this point here. So that helped quantify this. Another example that we studied with the same techniques was what is the effect of buffering in the grid. So when we will have a lot of solar energy in the grid, of course they produce when there is sun, so days like today and more in the middle of the day than now. So you need to store it. Is it possible to rely on the market that people would buy at very low price when energy is very short, is very plentiful, and release it later? And we saw that we analyzed the efficiency of the market, and we saw that the market works. So in the sense that there's an equilibrium price that is socially optimal. But it is not optimal in the long run, in the sense that the social optimum here is not the point that incentivizes operators to have the amount of storage capacity that would be needed. In fact, what happens is it's better for operators of storage energy to have a slight shortage, because if there is plenty of storage, then the value of storage becomes less, and so they're incentivized such that we operate in this region rather than that here. So that's the work I started to do. Now I had done one step into the energy systems. At the same time, Mario Paolone joined the EPFL here. I attended his inaugural lecture, from one inaugural lecture to an honorary lecture. Time goes fast. And I received Martin Vetterli put his hand on my shoulder and said, why don't you go to Professor Paolone and do a project with him? So which we did. We did a proposal for, I don't know, whatever bureaucracy uses those proposals in Bern, but that started a project on using communication systems for the electrical grid now. So Professor Paolone develops a sensor system that allows to monitor the grid, which is the major advance. So we built the network for that. So you see the network here. So it was a fantastic time. We had a full support. It was easier to get this, to have a network with full backup power, optical fiber, everything we wanted, than to have IPv6. We still didn't have IPv6 in the network at this time. We also imagine that at EPFL we can do this, because EPFL is EPFL, and if we ask optical repeaters and so on, we get them. But perhaps having communication links everywhere is not so easy. So we said, why not use Wi-Fi, directional Wi-Fi, and having two links, because Wi-Fi is notoriously not as reliable as a wired system, but two parallel independent links. So that was something that was developed by Miroslav and Maz and Dan. So I think the antennas are still there, but we will need to remove them by the end of July between two different buildings of EPFL. We measured the performance and proved that indeed, yes, you can achieve the quality of Ethernet over Wi-Fi directional links with redundancy here. This was I would say the reliability part. Reliability part is also with the estimation itself. Once you measure things, there's lots of noise in the electrical system. So I work with Lorenzo Zani and Rashid and Mario on denoising the system here. And that also became a large effort with all the people, Marco, Miroslav, and Sergio, Maz, Paolo Romano, and Tech, who all together developed this system. System research requires a lot of work, but it's a fantastic effort here. And Marco and Lorenzo and Paolo, who's not mentioned here, did a very successful startup out of those technologies here. We also did a course. The course existed, but I joined the course that Mario had started. So it was great fun to do this course with Mario, and just did the last lecture last week ago, so it's really sad, but this is how things are. And security, of course, is always looming ahead once you do that kind of thing. So Tech and Philippe, with the help of Jean-Pierre, who's not very far when you speak of security, helped us with doing an infrastructure that would help a system like this to be secure, in particular if it's attacked or there is an attack. For example, we were in 2011. In 2014, there was exactly such an attack in Ukraine. That was the forerunners of what is happening now against the electrical infrastructure of Ukraine. And the question is, of course, how do you reestablish the infrastructure? The techniques that are used are typically you have passwords that are allocated to devices. If the thing is attacked, it's quasi impossible to put it in place, so you should allocate credentials to people and not to device. So how to do that efficiently and in a way that's resistant to attacks and can be reconstructed when the thing is totally destroyed is one of the things we have developed here. We've also worked with Ola Svensson on how to do that on the fly, how to patch the software in such a system by removing some of the removing some of the PMUs to change the software. I mean, here we have wonderful technology because we can do wonderful things, but they have software, right? So as soon as you put software, you put the finger into, you open the Pandora box. If you have software, you have security. You need to patch it. You need to reinstall the software. So it's not like a system you put in place and you can forget about it. So optimal patching while not disturbing the operation is what we did here. Then we, because our curiosity is endless, so we asked the question, but we tried to secure everything, and then we observed there's one thing we cannot secure. There's a weird thing in the grids that's happening. That's the distribution of time. When you distribute time, you need very accurate time for all those things to happen. You need time at the accuracy of tens of nanoseconds, so much more accurate than we use for our computers here. You can use a GPS antenna, but still you need to distribute this over a network. And when you distribute time over a network, there's a weird thing that happens, is that you can never be sure whether your time distribution is correct, because there is a fundamental impossibility of distinguishing of measuring one-way delay. To measure the delay from A to B, you need an exact clock at A and B. But since you're measuring the delay to make the clock exact, there's a chicken and egg problem. It's impossible. So of course it is still possible, but this is solved by making some assumptions. And the assumptions is that the communication networks are fully symmetric. So the time it takes for the light to go from A to B is the same as to go from B to A, which most of the time is true. It's not always true when the wavelengths are different, but if the wavelengths are different, you know that they are different, so you know the ratio, so you can compensate for this ratio here. But since we are nasty, what if you do the following thing? You break the line, you make it longer in one direction, so that it is truly different in the other direction. So we made it. Sergio did it here. So that's a communication line with 1 kilometer of optical fiber that makes a difference of 4 microseconds. And those microseconds are used, and we can make 2 microseconds here. And then by being a bit smarter, by having not one thing here, but for example, 16 different lengths of cable, and by playing like you on a keyboard, you can do whatever delay you want, which has the effect of completely changing the measurements. So this is, for example, the regular measurements, how they should be perceived, but this is what you see after such an attack. So you can believe that the phasors here are changed, and with work that we did with the University of, with KTH and Marguerite and the group of Mario here, we analyze all this and show that those attacks are completely possible. The only way you can solve them is have enough redundancy in your measurement system to use anomaly detection. But if you don't have enough redundancy, there is no way. And what we've analyzed here is how much minimal redundancy that you need to do that kind of things here. And quasi-last, once we've done all those things, one of the projects that yet one more step, why don't we even do an electrical system? So this is what we did, this joint project with Mario Paolone called the Comelec problem that was funded by the Energy Turnaround NRP70 Swiss program here, where the idea was to use now real-time software to enable networks of the future, electrical networks of the future, to have extremely variable sources, for example, to fluctuating PV production, and how to use it optimally, for example, to link it with electrical charging stations, while preventing all the problems that could arise in the grid, for example, overvoltage or too high currents on the line, and also providing what is something very underground and not so well known, but support to the main grid. The way the main grid works today is that it has, not the way, but one of the stabilizing things in the main electrical grid is that as soon as we use more electricity, for example, if we switch on the light here, we use more electricity, then all the generators sense that there is more electricity being required, so they slow down, the frequency decreases a bit, and all generators are asked to evaluate the frequency, and if they see that things are slowing down, they put more gas for generators that use gas. This is how the grid is stabilized. But if we have a grid with a lot of PVs, they don't have gas to give, so you need to do artificial inertia into the grid. This is exactly what we do in this system. And the company was created with Lorenzo and Jagdish. And this project was done by a group of people. The originators was Andre and Lorenzo, and the group was joined by Jagdish, Nick, Pluton, who is finishing his PhD on one aspect of this grid called the shadow agent, Roman, who worked on the electrical station, Maz and Wajeb, who worked on the controller problems, and Fabrizio and Rika, who worked on solar and a number of other prediction systems, and Song, who worked on the inverse problems that are found in such real-time control systems. We had precursors of this that were done by Nadia and Dan on how to do something a bit simpler than that, but that would solve the voltage problems using techniques borrowed from, guess what, TCP congestion control for solving congestion control here. And now this is some of us when we visited in Hong Kong the electrical company trying to sell this system here. This was also related to, so we have a number of inverse problems to solve here. Some of those problems are using the techniques developed by Eleni Stai, who cannot be here today, that are also borrowed from Lyapunov stabilization found in communication systems. And in order to do this, you sometimes need to estimate the lines, and surprisingly, estimating the lines can be an extremely hard problem that uses statistics that were developed with Antoine Vienkel and Arpan, who can also not make it here today. So as you see, I've moved and done many steps. I fell into networks. I love them. I analyzed them. And then at the end, I finished with energy systems and electrical grid. But networks came back because 2018, network calculus came back. I received a message from Tony Pchienda, who is here in the room here, who said, hey, there are those guys at IETF, they need you, because the IETF was doing what is called time-sensitive networks. This is, in some sense, what Airbus had been doing 15 years ago. Now the whole industry starts having the same problems, automating more and more cables. So even a car today has a small Ethernet-style network. And so what Airbus did, the whole industry needs to do. Now this is becoming a big thing that is standardized at the IETF. So that call on the impulse from Tony, I joined the IETF group there, and they asked us to do a number of things. So for example, what they had proposed is new forms of regulations. Remember, the burstiness is one of the problems that cause problems, one of the features that cause problems into delays and buffer and so on. And one way is to analyze it simply. This is what AFDX and Airbus had done. Another way is to put systems that will remove the burstiness, like a damper or interleave regulators. So those new systems have come now, and we've analyzed them. And Ehsan did his PhD in a project that was funded by Huawei, and therefore patented by Huawei here. Ludovic, in a joint project with Marc Boyer and Alem Biftawi, who are, I would say, in the network calculus Airbus area, have also helped us work on better algorithms to find even closer delay bounds for a variety of systems. And Hossein has in particular analyzed some of the systems that are widely in use but were not in the catalog of network calculus tools here. Now, when you do those time-sensitive networks, you also tend to have packet replications. So we developed a packet replication like we did in the Smart Grid project. But this has side effects on the burstiness, because when you remove packets somewhere, it may be that all of a sudden the timings are completely changed. So this has been analyzed and put into the toolbox of network calculus. And the clocks, back to the clocks. We've spoken of the distributing the clock here. In industrial networks, we distribute the clocks, and with some precision. If you have extremely accurate clocks, there's not much of a problem. But in most systems, have clocks that have an accuracy of order of a microsecond, 1 microsecond is minuscule, you could say we don't care about it, but yes, we care about it. That may invalidate some of the regulators here. So we've analyzed that and incorporated that into the network calculus framework, and we were fortunate to have this RFC, so one of the standard documents of the internet. You see, the previous RFC was 2,000, 3,000. Now we reached the number 9,000, where we have devised how all those computations can be done for providing a time-sensitive service in the internet. And since in the internet, most of the industry that's working in this is, guess from where, is in China. So our network calculus book is translated in Chinese. So I was happy to see my name translated in Chinese. And if you I reverse translated it into using Google Translate, and then there is the word Switzerland in it. So. Voila, so I've abused of your time. I was asked to do 45 minutes, but since it's my last lecture, thank you for accepting this. I would like to thank many people who are not here today. I've just been one link in a chain of teachers. Everything I've done here, I've done it because I've been educated by a number of people. Not all my teachers were good, but I remember all the good ones, and they really had wonderful impact. They've made my mind the way it is. I would like to give special thanks to Rached Neime, who gave us the algebra lectures for the preparation to aggregation. And his courses were really wonderful. They are the examples that I've tried to imitate my whole life. So thank you, Rached, for this work. I would like also to thank all my PhD students. One of the very, very beautiful things at EPFL is that you can work with wonderful people who are your PhD students. So because, as Patrick said, I am organized, so I like to be organized. So I ranked you by order of completion of the PhD. And there's 10 in a row. So if you are here, you are 33. This is last 30. And
I finished before apparently.
I'm sorry. But as usual, you're better. Hossein will finish in 1 month, and Pluton in 3-4 months, and that will be the 35. And Sergio didn't do a PhD, but I still count him as one of my PhD students. So thank you to all of you. It was really fantastic, and it's really great pleasure for me to see you here. Also, thank you to all my postdocs. Patrick started as a postdoc, but quickly became a professor. And here are all my postdocs, so it's also been extremely fantastic pleasure to be with all of you, and became friend to most of you. So thank you very much for all this fantastic work that we did together. I would also like to thank my colleagues. I've mentioned some of them in my presentation today. So I would like to thank all of those. I cannot mention everyone. All the colleagues at EPFL. EPFL is a fantastic place. You just cross a few meters, you go to the cafeteria, you can work with people who work in biology, in medical imaging, in energy, and whatever. So it's a really fantastic place. The only thing that's missing is time, so thank you to all. Thank you also to my colleagues outside EPFL, Michel Benaim, and others who helped us work on a number of topics and who made the work so exciting. I would also like to thank all the PhD students. I've worked with a number of PhD students. I mentioned Lorenzo, Marco, and Lorenzo. There's 2 Lorenzo. And in other labs, Marcus, Marcus, and also in other schools for the excitement that they give and the motivation and drive. Now, the PhD students are TAs, and teaching is also a lot of work, a lot of effort, a lot of pleasure, if there's enough time to prepare it, like Rüdiger recalled. But thank you also to all the student assistants. We are very fortunate at EPFL to have this system that master students can help us and join the lab to help us. And usually they are all so enthusiastic about everything we do. It's when we're stuck somewhere in a paper that's rejected and then the master student comes and finds everything fantastic and great. So that's fantastic to work with people who love their work and who love our work. And also to all the bachelor and master students who did some interesting projects in our lab. And also to everybody who attended the lectures, because at the end of the day, I would not be here if they would not be there. I would also like to thank our admins, Angela, Patricia, who are serving us today. Holly, also, who is serving us for the English correction. And Danielle and Yvette, who left before. Also our sysadmins, so the people to whom we go and say, it doesn't work. And it takes too long. Why don't you fix my problem now? And they usually take us very efficiently and patiently and say yes, yes, and they always fix the problems. So I want to thank Yves and Marc-André, also Jean-Pierre, who left this organization, and Hans-Heinz Ziedler, who was our first system manager at the time of LRC. I want to thank EPFL for this fantastic environment. EPFL gives us, through the form of this fantastic campus everywhere, but also it gives us a lot of freedom to do things, except IPv6 on the student network. But if it's research, we could do practically everything we wanted, and some base funding to get things started. So network calculus would not have been done if I would have had to apply with Patrick, if we would have had to apply for an SNF grant, where we will explain that we will do network calculus, and then we will explain what we will do, and they were rejected the first time with reviewers who did not understand, or we did not explain well enough, or we should take a course on how to explain well enough to people who read very quickly one of your thing when they have hundreds of those to evaluate. So if we had to go through this would have never happened. So of course we need external funding, but the base funding is really something that EPFL has and is fantastic. I would also like to thank Martin Vetterli, Rudiger Oubanquet, and Jean-Pierre Hubot for their help at various points in my career. I was very happy to count on them for helping and solving some issues. Sylviane, Corinne, Jacques, and Jean-Luc, who helped us in their various positions, and always friendly and always great fun, and to be with them, not just to work with them, but also to be with them. And in general, the whole administration of IN, of computer science and the communication system department when they existed, and then when they became the NC school and the SSC and SIN sections and the EDIC doctoral school and the committees of recruitment of master students, and all those people who navigate the EPFL chaos for us and keep smiling when we ask things. And if we don't fill in a paper, they keep sending the email to recall that we did not send this. And they never yell at us. They always seem to be happy. So thank you very much for your efficient and friendly support. I've lived in France. I've been in a French university. I can say it's not the same. Thank you also to all those in central site operation. We sometimes complain about them, but there's been huge improvements over the years, and I think we've reached a level now where we can really thank them and be very happy for everything, the way it's happening. Thank you also to the cleaning and food services for the men and ladies who come in the evening on the early morning to clean my office when I came with my boots because I bring my dog and it rained, and they clean it, and they never complain, and they smile and they chat, and thank you very much. And the food services, in particular for all the cafeterias where we usually go, and they are always also smiling and seem to be happy to see us here. And also to Mark and Deirdre, who organized this event so professionally today. And last, I would like to thank one person with whom none of this would have happened. Well, I would like to thank also my children, because with my wife, they made the nest that made it possible to concentrate on research, because when you come home, things are so nice. And I would like to also thank all my grandchildren and all the babies to be born in the world for taking care of the things that are coming. Thank you.
Thank you so much, Jean-Yves, for making us part of this exciting journey. That's the longest applause I've ever heard. Now, anyone here wants to ask the question?
And you will notice, okay, what did I say? Well, I guess I'm here to represent the EPFL chaos, as you said, right? Sorry. But I'll say a few personal words before going to the formal delivery of the diploma, the Professor Honorary, with the dedication. So I had the chance to interact with Jean-Yves from day one. When I touched the ground at EPFL, well, it was a bit more complicated because I touched the ground I started on 1st of August, right? And so, I mean, just to show you how EPFL has evolved, good or bad, I don't know, you will, see for yourself. So I came from the US for the 1st of August, and I remember being Swiss that it was maybe a holiday. So I called up EPFL. I said, do I have to show up on the 1st of August, or could I show up, maybe on the 2nd? And the answer from central administration, was, you know what? In August, nobody's around. Just show up whenever you want. Okay? But I guess I'm still here. So, all right. So, but very quickly, actually, we had, of course, interacted when I came for interviewing with Jean-Yves and Jean-Pierre, right? And but from day one, I have been very impressed by Jean-Yves for a number of things. I made a list here, pretty long list, as you can guess. The clarity of thinking, and you can see this in his lecture, right? I mean, he's laser sharp. He knows exactly where he goes, takes no prisoners, okay, and gets to the result. So that's number one. And the second one, which is amazing for, somebody that is that smart and could do very esoteric theory for no good reason, he actually always chose very relevant problems. You could see this. I mean, it ends up in patents, it ends up in startups and so on, yet it is very sophisticated mathematically. And this is really what I like about, this sort of work. And thank you very much for having done it. Then it's his pedagogical skills. I didn't have the chance to follow one of your classes, but many of my PhD students took classes from you, and they're always super impressed. Some of them were TAs for you, and they, of course, loved working with you as TAs. And so thank you very much, because our first job is actually teaching. The second one is mentoring PhD students, and both of these you did exceptionally well. Which brings me to the dedication to your students, right? You were known to work very closely with the students and to give them outstanding, skills for the future. And I know it firsthand because I had the chance to work with some of your former PhD students, right? even now in central chaos, right? And these are just, the best people you can find. So thank you very much for having trained this generation of fantastic students. Then you're also very committed to the institution, okay? And not all superstar researchers are very committed to the institution. I know this from Central Chaos. And I have to say, when Jean-Yves says he's going to do something, comité, machin truc, he does this to perfection, like everything he does, right? And for this, I would really like to thank you. And last, but you know this, he has very low tolerance for BS, okay? which is a great thing, right? And now, the contributions were, presented in his broad panorama. I'm not going to add anything to this, but I'll just relate a couple of souvenirs. Sorry, Central Chaos is also about anecdotes. And so the first one is, things have always been better, right? That's classic. And so you did mention the doctoral program. So when we showed up, there was no training of PhD students. Okay? This is unbelievable, right? For those of you who are in the room as former PhD students or current PhD students, I don't know how the place could work, actually. So, well, Jean-Pierre said, when I asked him how is EPFL, he says, l'EPFL est incomparable. This you can read at least two ways, right? Anyway, so we decided to make it incomparable, truly, and we started a doctoral program. And for this, we wanted to have first-year fellowships. You probably remember this, right? And so a bunch of us, Jean-Yves, Jean-Pierre, we went to see the president at the time, Jean-Claude Badou, and we said, we are, listen to this, we are ready to give up part of our dotation to pay for a doctoral program. So we have fellowships for the first year. So we had very generous dotations at the time, right? It has been, only going down since then, especially now, right? So, blame, you know whom you have to blame. So we told to Badou, we said, we give up half a position, he will pay, and so on. So Badou thought about it for a while, and then he said, well, this is going to be, administratively complicated. I'll just give you the money, right? Now, sorry to say, this trick doesn't work anymore, okay? So you can try, but, okay, so the second one, more serious, is the pleasure I had to work with Jean-Yves, Jean-Pierre, and many others with the NCCR mix, which was, I think, one of the early success stories at EPFL of, a bunch of professors working together, raising, substantial third-party funding and having a real impact in many dimensions, actually. I think it influenced all of our work, and it was really doing something new, going into, unknown territory and so on. And this is something that we had learned from, the ways the US works and does fundraising and goes into uncharted territory. And this is certainly something that is one of my best souvenirs from doing research. And then I want to, that's a personal remark. Jean-Yves actually speaks Swiss German, right?
It's a bit silly.
Say again?
It's a bit silly.
Yeah. So not only does he speak Swiss German, he's a great singer, as you probably know. And he did me the honor to sing a Mani Matter song, and I'm going to say it in Swiss German, Wenn es gut geht. Okay, that you probably learned from Annelies, which also shows that Jean-Yves has his heart at the right place, right? The song is about social inequality. It's a very subtle sort of song, which sort of points out to we are in a bad spot. And when it was done in the 60s, or 70s, it wasn't as bad as it is today. I think we are facing a very unequal world, and we need people like Jean-Yves who have the heart at the right place. So thank you. It's one of my best souvenirs here at EPFL when you sang this song. Good. So it has been an immense pleasure to be a colleague of yours. And it's also an honor to have fantastic people like you at EPFL. Thank you very much, Jean-Yves. And I will read, the formal thing here. en témoignage de reconnaissance pour ses contributions scientifiques exceptionnelles et à la rigueur de ses résultats, en particulier dans le domaine de la performance des réseaux de télécommunications, pour son engagement infatigable dans le fonctionnement de l'institution, notamment dans la commission d'enseignement ainsi que dans la commission de promotion interne du personnel académique de la faculté. Central must have written this. Pour la qualité remarquable de son enseignement et de sa pédagogie et pour son soutien sans faille au développement d'une nouvelle génération de chercheurs et praticiens. Thank you very much, Jean-Yves. Merci beaucoup. Encore une photo formelle.